This is going to take you through what you need to know about electric fields, the particles and waves part of higher physics. So we're going to be looking at the idea that electric field causes a force on a particle, what the shapes are of the fields between different charged objects such as point charges and parallel plates, and then the direction of movement and the force caused by that. Quick video from a Swiss science centre. You've probably done this experiment or seen it earlier on in your school. I've taken the audio off, but you can see that the child here is being discharged and is completely unaware of the fact that he's got a lot of positive charge, which is causing everybody in the audience to have a giggle. So you can see that when the child is discharged, then the force between the hairs stops there. And then somebody shows a mirror, and you'll see the expression on his face there. And the sparks are electrons actually moving across the gap. So it's also quite nicely shot because it's backlit as well there. And lastly, a little bit of chemistry. There he is, he's seen his reflection, hence a smile. But that strange air smell is something that those of you who are interested in chemistry could spend a bit more time on. So there's the inside the Van de Graaff. There's the conveyor belt, which is taking electrons off the cap and leaving an overall positive charge there. The spark there is due to ionization as electrons move across the air. What we're interested in here is the actual electric field that's around it. So I've got this drawn here, and the key thing is that if you put a positive charge in that electric field, it experiences a force in the direction of the field lines. So often think of this in terms of cause and effect. The field lines here are invisible. You don't see those around the Van de Graaff generator, but you do see the force when something that's got the same force is pushed off in the direction of these field lines. And it's the field lines as the cause, but the force is the effect of the field lines with a second force. So let's just have a look at how you would be drawing these electric field lines. First thing is that they always start at a positive charge and end at a negative, or if there's no negative charge, they'll go off to infinity. And they tend to separate out once they left the charge. You'll never get them meeting or crossing, and if it's an even surface, then they will spread out evenly. So that's with a positive point charge. If we do the same thing with a negative charge, again, it starts at positive but then goes to negative. So all the field lines are coming in from infinity and ending up at that negative point charge. If you put two together, then they start from the positive charge and will either go towards the negative or just out to infinity, eventually, funnily enough, coming back to the negative charge. Two similar charges, the lines never meet, they never cross. So in this case, they're coming in from infinity, meeting the negative charges, and there's no join in the middle there. Lastly, if you've got a parallel plate capacitor or two parallel plates like this set up, positive and negative charge, then the electric field goes between the two in regular straight lines. And the spacing of the field lines tells you the strength of the field, and in this case, the strength of the field is an even or uniform field. One thing that you're not asked to do at higher is to think about these end effects here. So beyond the end of the parallel plates, the electric field tends to bulge out. That's not required at higher. So you are going to be answering some questions on the Google form, but first of all, pause the video and just make a note of the diagrams of these electric field lines in your notes jotter or on a piece of paper. You will be expected to be able to draw these kind of patterns. So we're going to pause here while you answer some questions after you've copied these out.